What's different about it? What does that word nuclear mean? It has to do with radiation, sure, but just that word like nuclear, what does that mean? In absent any other context.
Explosive.
Not really. Nuclear just means,
My headache comes out.
sure, that's what we associate with it. But it's really just chemistry of the nucleus. Right? Which is the protons and neutrons. The reason that's so different from what we've done so far, if you think about all the reactions that we've talked about, what are they the chemistry of? Electrons. So we talk about gaining electrons, losing electrons, sharing electrons, breaking bonds with electrons, making bonds with electrons, electrons being shared unevenly in polar bonds, like all the stuff we've been dealing with for the last however many weeks is all electrons. And that's really the basis of chemistry. So we're going to take a break from the electrons now, and we're going to talk about the chemistry of the nucleus, what happens inside the atom. Because the things that happen inside are totally different from what the electrons do. Okay. So let's get some terms straight first, and then we'll get into some. And so I've got a bunch of stuff here, got a bunch of radioactive stuff, and we're going to look at it and learn some things about it. So first, let's talk about this radiation. Radiation is kind of a scary concept, I think. Maybe, right? We think of it, we associate it with kind of bad things. And in some instances, that's absolutely true. But it's actually a much more general term than that. Radiation simply refers to the emission of energy and particles. So just something emanating out from something else is radiation. So radiation really describes all kinds of stuff that is not at all dangerous. Things like light. Light is a form of radiation because energy radiates out from a light bulb, and that energy is in the visible spectrum, and so we see it. But it also describes, yeah, so microwave radiation is another type of light. Microwave is a type of light. And those frequencies of light also emanate out from some sort of generator of microwaves. You've got a generator of that in your microwave oven, but also things like cell phones work on microwaves. It's just another type of light. Radio waves, another type of light. So radio waves would radiate. But then also more harmful things like X-rays or gamma rays or some of the stuff we're going to look at today, beta particles, alpha particles. You can have electrons shooting out from something, and that's a type of radiation. Many years ago, there used to be these computers and TVs that were like big and not flat. Does anybody remember those? Yeah. And so that's how those worked. But they would shoot a beam of electrons, and so you had to have a big space because it was literally a tube shooting electrons at a screen, and it would kind of go back and forth like this. That's how those things work. So that's electrons radiating out from a source. So those are all types of radiation. There's nothing inherently good or bad about radiation. It depends on what is doing the radiating. Is it something like visible light that's not harmful, or is it something like gamma rays, which are harmful? Okay, so let's then talk a little bit about that dangerous part. The dangerous stuff is what we call ionizing radiation. What do you think that means? What does it mean to ionize something? You know some chemistry words now. What do you think that means? Kind of, yeah. What were you saying?
I was saying give it a charge.
Give it a charge, right. Form an ion. Yeah. So it's radiation that can form ions. And the way that it does that is by knocking off electrons. So ionizing radiation is radiation with enough energy to remove electrons. From atoms or molecules. So when we talk about radiation being strong enough to cause burns, that's one example of that. It's destroying tissue by knocking these electrons off. When we talk about radiation as being cancer-causing, something like that, we're talking about electrons being knocked off of DNA, which causes it to bind to itself in ways it's not supposed to, and then cause all these other problems. So these are the types of radiations that can cause problems where they remove electrons from atoms and molecules. And anything with higher energy than ultraviolet light can do that, which is why ultraviolet light can be dangerous, and then X-rays, gamma rays, those are all types of high energy light that are ionizing radiation. Some of the particle radiations that we're going to see today are also ionizing radiation. Okay, so that's radiation, ionizing radiation. The last term we're going to look at before talking about these individual things is radioactivity. Radioactivity is the name given to the process of an atom breaking down and emitting radiation of some sort. And this is kind of the key to all the chemistry in this chapter, or the description of the chemistry in this chapter. This describes the reactions that we're going to see, and you can kind of hopefully tell how they're so different from what we've seen so far. Electrons just don't have enough energy to do this kind of stuff. So electrons do all the stuff we've talked about, but nuclei are held by such strong forces that when they break down, the energy that they emit is much higher. And so that's what we're going to be talking about the next couple hours. All right. So let's remind ourselves, because we're going to use this a lot, of this way of writing an atomic symbol. So if I write iodine, I, and I put two numbers by it, what do those numbers mean? We did this way back near the beginning of class. So does anybody remember what that means? Yeah, so which is which? Which part's which? No. Close.
No, wait, okay. Welcome to the atomic number. Yeah, the 53 is the protons.
Okay. Yeah, so if we look at the periodic table and find I, it's number 53, right? So that's the atomic number. That's down here. So you got there eventually. It's good. Should we do all our exams like online, so you can just like keep hitting answers until you get the right one, like a online quiz or something? Like, yeah. What kind of element are you? Okay, so what does the atomic number describe? What does that tell us? What is it that defines an atom? The number of protons, yeah. The atomic number is the number of protons. So then what is the top one? Yeah, somebody said it.
The sum of the protons.
Yeah, this is what we call the mass number, which is the protons and the neutrons added together. And remember, it's not the number in red on the periodic table, that number is an average of all of the ones that exist. So if we're looking at one particular atom, one particular isotope, we might say iodine 131, which describes a particular set of iodine atoms that have 53 protons and 128 electrons. No, 178 electrons, right? Is that right?
Sure.
Subtraction is hard, yeah. So yeah, so that describes that particular thing. Okay, so let's keep that straight because the reactions that we're going to see use those symbols to help us understand what's going to happen. All right. We go through a series of these types of nuclear reactions. We're going to look at what the reaction looks like on paper, what the particle is, and then we'll dig one out and we'll see what kind of behavior it has. So the first one is called alpha decay. These particles are given these kind of weird names like alpha particles, beta particles, X-rays, because when they were discovered, nobody really knew what they were. You could see them, you could kind of measure them, they were detectable, which is how they were discovered, but we didn't really have the tools or the theory to really explain what that thing was. So they have these kind of generic names. So that's the Greek letter alpha, alpha decay. And alpha decay is the process by which an atom loses an alpha particle. An alpha particle has 2 protons and 2 neutrons. So it's a little ball of stuff with 2 neutrons and 2 protons. That means that it can also be known as a helium nucleus, because a helium nucleus has 2 protons and 2 neutrons. So the alpha particle is drawn as a helium nucleus like this. It can also be drawn as this, but it's not as common, where you say alpha instead of helium. But because it literally is the exact same as a helium nucleus, we can just call it helium. So here's what a reaction might look like that does this, that undergoes alpha decay. So we would take a particular isotope that undergoes alpha decay, and because it undergoes alpha decay, that means there's only one starting material. There's only one thing it starts with, and then it decays, it breaks apart from there. So it breaks apart into one of these alpha particles, and then this other nucleus, which is thorium. Now, the neat thing about these reactions is once we know what type of decay a nucleus undergoes, we can figure out what the other side of the equation is supposed to look like. So all we have to know is that uranium-238 undergoes alpha decay, and we can write the rest of it. How? Because we can look at the numbers. You see that? So if it's losing 2 protons, that means the particle that's left over must have 90 protons left. And similarly, if we're losing 2 protons and 2 neutrons, that's losing 4 from the total mass. So there's 4 fewer in the mass number. So in that way, these equations are pretty easy, because all you have to do is make sure the numbers match up on both sides, and you're good. So let's try it. Let me see what kind of alpha emitters we have. right, so this is a thing called a Geiger counter. This is a device for measuring radiation. So for the first, we're going to use two different types. One is connected to your computer, and one is just this guy. Although it looks like the probe is not here. Let me see it. Oh, it's in there. So what this does is has a electrical field inside that detects when these particles are hitting it, because the particles are charged, and so they create a really, really small current. So there's a high voltage in there, and then when these particles come, it can detect that change in current, and then it flips onto this thing. This is obviously a pretty old one, but still works. All right, so here's the counter. Take out my radioactive stuff. So the alpha emitter here is polonium-210. This is actually plastic, but that little metal foil on the bottom there, that's polonium-210. So this is radioactive, an alpha emitter. So what I will see is, so a little bit, put that down on the desk here. And when I get this thing fired up, hopefully we'll be able to hear some stuff coming out of it. We'll see. All right, so you hear that coming out? Every once in a while, a little blip. That's radiation that's coming through the air. There's always radiation all around us. It comes from space, comes from rocks, comes from building materials. There's always a certain amount of radiation that's known as background radiation. It's just something that is all around all the time. It's that same kind of ionizing radiation. There's not really anything we can do about it unless you want to just live covered in lead or something. So anyway, if I put this thing up to that, we should hear more of a response. There it goes. So you hear that? It picks up a little bit?
Yep.
That's the alpha particles hitting this thing. Now notice I have to pretty much put that thing right on top of here. As soon as I move it up to like here, nothing, right? Just not doing anything. And that's because alpha particles are big, relatively speaking. So let's look at that reaction. Let's see if you can do it. Polonium-210 undergoes alpha decay. So you can write that reaction. So you got to start with that polonium-210, which that tells you the mass. Remember that in that kind of a notation. We can find the atomic number from the periodic table. And then see if you can write what comes up on the other side. We got a reaction there. So what did you come up with for the product besides the alpha particle? Lead? Yeah. So polonium is 84. We write that alpha particle first, and then we just subtract to figure out what's left. So we've got 82 on the bottom, and then 206 on top. We look up at the periodic table, 82 is lead. And that's it. There's no balancing or anything because we're only looking at one atom at a time. And that's alpha particles. So alpha particles are pretty big, like I said, which means and we would say they're not very penetrating, which means they don't get through stuff very much. They get blocked easily. And so what we saw just there with the example of the little bit of polonium is actually something that comes up in that lab. So let me pull up that lab. We can do that right now. Check that schedule. Is it so? Make sure we're in doing the right stuff here. Yeah. So we're doing nuclear chemistry, acids and bases, and then next week we're scheduled for this, but we're actually going to do number 12 because we're going to miss the Wednesday. So, and that's it. We're almost done. Okay, so you can do this with the questions and stuff on your own. We'll go back and look at some of that. But one of the things that we do in this lab is comparison of radiation with distance from source. So how far away do you have to be before, or how does the radiation change based on how far away you are? And actually, I'm going to download this and save it. I'll put it in our notes folder so we can annotate it and you can get that data. What? Why can't I? No, it isn't. Okay, well, anyway. That. Okay, sorry, going on to this thing. So the lab starts here. And what we're going to do is look at the comparison of radiation with distance from source. So we're going to kind of standardize things a little bit. We're going to use this thing to hold the detector. And then I'm going to use this for the isotope. So I'll get my viewer. I'm going to put this up here, right by the thing. That's actually about 10 millimeters down. So let's do this. So here's the program we're going to use to measure the radiation. It's the exact same as that thing, except we get to see the data getting logged here. So if I put this right down on top of that source, it's sampling every second how many counts it's getting. So the way we record this, because it's kind of all over the place, is we just kind of pick where we think the averages of it going. Now, we really should probably get a new sample of this because it should be much higher. As we'll learn over time, these things lose their radiation because they just decay and there's just not stuff left anymore to decay. But I don't know, what do you want to call that, like 3 or something? So we might say that's 3. So then if we put it in this thing about 10 millimeters down, so a centimeter down from the source, you can see it's down to like nothing, right? So even just that centimeter of air pretty much squashes all the radiation. And that's because the alpha particles are really not much smaller than air particles. So they hit the air particles and the energy gets absorbed or they get diffracted or something. So we're still getting a couple counts. I bet if I put that down one more, we'll really get nothing here. Let's see. Yeah, so now it's way down to 0. So we might record that as background radiation is like 1. At 10 it was 3. 20 it was back to 1, and then, or 20 it was back to, oh, so we didn't even need to measure right there. It was pretty much back to 1, so that we really didn't see much there. And if you weren't paying attention and you're doing this lab by yourself, which people have done in the past, they go and keep measuring every other one beyond that, when it makes more sense to just say, okay, here there's nothing, so these other ones is also going to be nothing, right? So nothing all the way through there. Okay. That. All right, so next is beta decay. And this is a reaction where you decay a beta particle. A beta particle is an electron, like just a regular old electron. So we write it usually like this. Oops, not like that, like this. So we say the atomic number is -1 because it has a charge of -1, and it has a mass of 0. Now electrons have mass, but the mass is so small compared to neutrons and protons that it's effectively 0. So it's okay to call that 0. Sometimes this is written with the beta for beta particle. All right, so this one's small, and this is a little bit weird because, again, this is a nuclear reaction. So we're saying that in this nuclear reaction, an electron comes out of the nucleus. And there are no electrons in the nucleus, right? So that's kind of a weird thing to have happen. What really happens is a neutron splits into a proton and an electron. So a neutron has no charge, 0, but it does have a mass of 1. And the neutron becomes a proton and an electron. If you look at the numbers, the charges and the masses, you'll see that that actually works out. 1 plus -1 is 0, and 1 plus 0 is 1. So the neutron becomes a proton and an electron. And that means that a beta decay equation is going to work in the same way that the alpha decay one did, but now we have to deal with a -1. Let me show you an example of that. Carbon 14, which is the carbon that's used for carbon dating, is an example of that. So we say this undergoes beta decay. Beta decay produces a beta particle. And then what else do we put there to make it add up to 6 and 14? So what plus -1 is 6? 7, yeah. So we actually put a bigger number there. It seems weird that something would decay but then get a bigger number. But if you go back to what just happened, that kind of makes sense, because a neutron, which isn't part of the atomic number, becomes a proton, which is a part of the atomic number. So the atomic number goes up by 1. The other thing you can do is just ignore all the stuff in the background and say, okay, the numbers have to work out. So whatever makes the numbers work, that's what we're going with. And then what plus 0 is 14? 14. So the mass number there doesn't change. Because the atomic number has changed, we've made a new kind of an element. What have we made? Nitrogen. Yeah. So that's beta decay. All right, let's look at our beta emitter here and see what we got. Let me put our polonium back too. Cameras. All right, our beta emitter here is strontium 90. So if we just look at it with the old one first, just to see if it does anything. We got a lot more radioactivity there, right? Look at that. Kind of satisfying. The other thing you can notice here, remember you saw that foil on the other one? This one doesn't have that. And the reason is because the alpha particles are so non-penetrating that if they made it in plastic like that, they wouldn't get out. And so you'd never be able to measure anything. Beta particles are smaller and they can make it through plastic because they're only the size of an electron. So that's a little safer. Now we can not worry about accidentally touching the material. So that's on there. Okay. So beta particles are smaller. They're also a little bit faster. So that all taken together, they can make it through stuff. So they're a little bit more penetrating. They can get deeper into stuff. If we once again start our collection, this is now 10 centimeters back. And we're getting a pretty nice signal up in the 50s or more coming out of that. And that's not an indication of the type of particle. That's just the isotope. It might be a little bit newer. It's just more radioactive. It has more stuff coming off of it than the other one did. So every one of those counts is a beta particle hitting the emitter. So if this thing is, 60 counts per second or whatever it is, that means every second about 60 of those 60 nuclei are decaying and hitting that detector. So let that run for a second and let's look at that equation. That isotope is strontium 90. So see if you can fill in the rest of the equation for the beta decay from that. Got some equations. So you got to look up at the periodic table, see that strontium is 38. And then on the other side, you write the beta particle. And then whatever is left over. So -1 plus what is 38? 39. And then 90 goes on top. We figure out what that is. It's yttrium. So every time we see a count on that other device, this measurement, so 60 times a second, a strontium atom is turning into an yttrium atom. So we're changing from one type of an element to another just because it's decaying. So let's average that out and say it's about 60. Does that sound good? Yeah.
I was just gonna ask, like, for the beta decay, we're basically gaining 1 to the atomic number, no matter what it is.
Yes. Right. Yep, that's all that's happening. Okay, so we can fill that in. Here again, our beta particle, again, our background radiation was like 1, and then here we're going to say 60.
How long does this decay last? Yeah, just keep going.
Yeah, well, we're going to talk about that. We can measure that in something called a half-life. So over time, it will decay, and eventually it'll all be gone. But so it does decay over time, and eventually it'll be gone. In something like this, I mean, even though it's only a tiny thin film of this actual material, that's still so many atoms that it's going to decay for a while.
Does the new substance that's created start decaying as well?
It depends if it's radioactive or not. So in some cases, yes. In some cases, no. What was this one? What yttrium 90 is maybe? I don't know. I don't know if that's a stable isotope or not, but you could look it up and see. All right, so by moving it an additional 10 centimeters down, you can see we've dropped the radiation to, I don't know, 30-ish. If we take it down another 10 centimeters or 10 millimeters, so now we're down in the teens, right? Call that like 17. And so you can see the beta particle has a little bit greater ability to penetrate through the air. This experiment gets a little bit messed up because as you move it down, it's also not aiming as well because it's emitting in all directions. And so what's being captured by the detector that's right on top of it, the further you move it away, the more stuff is shooting out to the sides and not getting to the detector. So yes, it's not getting as far, but also there's that effect, that diffusion effect. So that's down to like, call that 11. Now down in the single digits. And so on. That's probably, let's see where that's going. Let's see how far we can get it to really be nothing. So one more down. We're still getting some counts. Another from there. Still getting some counts. So air is not really an effective shield for this stuff, as you can see. All right, the other part of the lab. Here, why don't I? Maybe way I can do this more. Yeah, it's kind of hard to see. The other thing that we're going to look at here is what types of materials can shield this. So the alpha particles, you can probably guess, everything just shields that. right? So anything is pretty much going to be 0 there. But we can look at some aluminum, some plastic, and some lead and see how well that shields the beta materials. So we're not going to look at all of them. We'll just take a sampling of them. But I've got a set of stuff. So what we want to do here is look at basically how thick can we get before we lose that radiation. So I've got this backup at the top, and I'll reset this thing. Okay, so there's our initial radiation again. Oh, it's not quite set. I was gonna say it looked a lot lower than it was before. There we go. Okay, so back up to where it was before. And I'm gonna put a thin piece of aluminum foil right on top of this thing. Oh, you know what, I can't. So we have to start one down. So let's get that baseline again. That's about 30 something. If I put this aluminum foil on top of it, let's see what happens to the radiation. So nothing happens, right? See that? Maybe it's a little, no, it's jumping back up. So yeah, nothing really happens. It's not attenuated at all, which means those beta particles are making it right through the aluminum. Aluminum's denser than air, of course. But what if we increase that thickness of aluminum? So now that was a 4.5, a 0.7 mil plate. Is that milli inches? I'm not sure what that is. Let's see if we up this to like from a foil to a plate, if we can get some attenuation there. Yeah, so now you can see that starting to go down. And let's see how thick that plate can get. If we go to our thickest aluminum we have, which is 1/8 inch aluminum. We can essentially block all the radiation. So now there's enough material there that those electrons are hitting other stuff before they get through it. But we can try all those aluminums and find like exactly where that happens. Now let's check the plastic. Let's take our thickest plastic, not that thick, but the one that's thickest plastic that's in here. And then we see some attenuation there as well, right? Not as much as the aluminum, because plastic's not quite as dense as aluminum. All right, now let's take a look at lead. We can take our thinnest lead here, which is a 0.032 inches. So just for comparison, here's the 0.032 inch aluminum plate. So definitely blocking something. It's putting it down like in the teens or just below 20, something like that. And now the same thickness, exact same thickness of lead. And it's blocked now, right? And that's because lead, if you look, number 82, is a lot more dense than aluminum. A lot heavier. Each atom's a lot heavier. So that means the nucleus is bigger and there's more stuff for that electron to hit on its way through. And that's why we use lead as shielding for radioactive stuff, because it does such a good job of it. Okay. So when you fill out that lab, you don't obviously, you won't have a number for every one. Just write down in your notes that you have a general idea that basically what we found for the beta is that the aluminum was quenched here. So if we had around 30 for 0, it went down to like 15 at this one, and then down to 0 by the end. The foil that went through, we didn't check the other foil. And then the lead, when they're at 0 inches thickness, which is nothing, it was about 30, and then we put in that thinnest lead at 0, and so the other ones are going to be 0 as well. Okay. And as long as you have enough data that you can answer the questions, which that is going to be enough data for that, that should be fine. Okay, so we've done alpha decay, beta decay. Next one, we'll look at gamma decay. Then we'll take a break and come back to the rest, talk about half-lives. This one's kind of different from the other two because there is no gamma particle per se. There's instead gamma rays. So gamma rays are high energy light, which means they don't have mass, they don't have charge either. They're just really high in energy light, so kind of like X-rays, like more or higher energy light than X-rays. Our gamma rays. And so we write them as 0, 0 with a little gamma. Because they don't have charge, they don't have mass. They're just light. So then how do reactions work if it's just 0, 0? Well, when we talk about gamma decay, we don't write the equations in the same way. In other words, we're not just looking for changing the numbers. What happens is something decays via another process to what's called a metastable state. And there's a little m put up there by the atomic number. Meta means partially, so metastable is something that's partially stable. It's just a nucleus that it's not quite in the form that it wants to be in. It's a little bit higher energy. And it loses that extra energy by emitting a gamma ray. When we write this equation, we write the gamma ray as coming off, and then the nucleus loses its M to become just regular, stable nucleus.
I think it's supposed to stand for what?
Metastable. Let me put that here. Metastable, not totally stable. This is technetium-99m, which is a really important, medically important isotope. There's all kinds of places that just make this stuff because it's in such wide use. The key component of, or the key characteristic of gamma rays is they're very, very penetrating. They get through lots of stuff because it's just really high energy light. That's the background radiation. So like when I had this thing, that's not all the background radiation, but that's most of what we're seeing here. And we just kind of wave this thing around and we get a flick every now and then. Some of that is gamma rays that have come from space, from like deep space, because they just get through stuff. They can go through, well, space, obviously there's nothing there, but they can go through materials. They go through the walls, they go through atmosphere, get through planets, all that kind of stuff, because they're so small. When we talk about getting through things, remember our atomic structure. Remember that atoms are mostly empty space. You've got your nucleus in the middle, and you've got your electrons, but the distance between the nucleus and the electrons is really, really far in like atomic scale. So there's a lot of space for small things to get through. And that's how some of these things can get through some of this stuff. So let's look at some gamma rays. So, how this is used in medicine, there's a few different ways it's used, but one of the ways is they can put it in you, and then depending on how it's processed, they can image it. You can basically measure the gamma rays coming out and see where that stuff is going and what's happening to it. And that'll give you a picture of what's happening in certain organs as this stuff makes its way through your system. Now, because it's radioactive, you have to be really careful. So if you're doing that kind of work, they'll usually make you go to a facility and stay there, and they'll like collect all of your urine and poop and stuff because it's all hazardous radioactive waste. And then once you're not radioactive anymore, then you can go home. But the other reason this isotope is used is it has what's called a short half-life. We'll talk about that later. Basically means it decays quickly so that you don't have to stick around for that long before it's all decayed. So the gamma emitter we have is a cobalt 60. And a stable cobalt 60. Doesn't look like anything, it's just hidden inside there again. Make sure this has enough stuff still. Yeah. Okay. Didn't hear that. It's definitely needs some gamma rays. Up in there. And we'll see how this thing goes. So all right, so we've got a good baseline for where it is at that about 10 centimeters down. Let me scale this a little bit. Oop. Just like that. So, all right, so we're around 25 or so. Yeah, that's down 20 centimeters. Oh, so there's still. Let's see if that changes anything. Let's put it back up right underneath it. It's just 10 centimeters away. So it's just 10 centimeters away, that's like 30-ish. Okay. And if I drop that down 2 spots to 30 centimeters, you do see that attenuation. But for gamma rays, that's really not from it blocking the air, that's from this eating effect, so that it's now dissipating in other directions besides going straight up into the tube. So eventually it will be attenuated, but again, that's more, part of it is from the air, but mostly it's from just that effect. And you can see, even at the very bottom, it's still giving enough of a signal. It would say, thank you, it would say it's above the background for sure. Okay, let's pop this back up to the top and look at how these different materials block this stuff. So we're starting around, whatever that is, 20-ish, less than that, more than that, less than that, more than that, 19. Let it stabilize a little bit, something like that. So what you would really do if you're trying to do good measurements here is you'd average it out over some amount of time and call it some kind of number. All right, so let's try some of ours again. Let's go with that aluminum that that 0.032 aluminum that we attenuated the beta particles with. And we put that in there. Excuse me. You see any change really? No. Really nothing, right? Let's go to that 1/8 inch aluminum. Really thick aluminum. So what do you think? Not really, right? Still kind of just bouncing back and forth. So because aluminum's not dense enough, there's a lot of, or not that dense, there's a lot of space for those gamma rays to get through, and they're just getting right through it. So aluminum does not effectively protect against gamma rays. All right, what about that thinner lead, that 0.032 lead? Because lead's much more dense, so we might expect to see something with that. So, maybe a little bit. It's not quite hitting the peaks that it was, but it's basically in the same kind of place. So even that lead that completely killed all the beta particles is only slightly attenuating this one. It is bringing it down a little bit, I think. So if we go up to 1/8 inch lead, so this is as thick of lead as that aluminum was. Bring it down again a little bit. I think, but it's still getting through even with that big, heavy, thick lead. And then we've only got one thicker than that, which is a 1/4 inch lead. And this is like pretty heavy stuff. Doesn't even fit. Let's see if I can do it this way. There we go. Is it on when I covered it? I can't tell.
It's a positive effect.
Don't get into your eye.
Yeah. Yeah, so you can see, again, it's bringing it down a little bit, but still, most of it is getting through there. Yeah, so those gamma rays are getting through. So even that kind of lead is not gonna effectively shield you from all the gamma rays. All right. All right, so we learned here that these are highly penetrating. So that's good and bad. They're highly penetrating. It means they can also go through your body. So most of the gamma rays, if you were exposed to gamma rays, most of them are going to just make their way through your body with no problems because they mostly make it through stuff, especially stuff that's not that dense like the atoms that make up your body. The problem is when there's a high, really, really high concentration, a lot of gamma rays coming at you, some of them are going to hit you and they're going to do a lot more damage, or they're going to be able to do damage deep inside you because of their penetrating ability. Okay, so that's those three basic categories of nuclear reactions. You can practice some of those equations. Let's take a break, and when we come back, we'll talk about measuring radiation and half-life. And then we'll be done.
Because, oh my God, both of them are terrible.
It's just entertainment.
I know, our country's a joke, like, not gonna lie.
It's
shameful.
I love it, but you know, it's a great country, but it's completely shameful. Wonder what-
Other people, I know. I know that's what I was
America,
like.
land of the free, doesn't really sound like it.
No, it really hard. Oh.
So excited to vote for it? Don't forget,
Dude, my moral compass is just like, all right, where do we go with this one?
Yeah. Sure.
yeah, don't forget to vote. In Illinois, you don't have to be registered ahead of time, so even if you didn't register, you can vote, you can vote. What?
Yeah, you're good.
Yeah, so let's do some chemistry so we don't have to think about it for another couple hours. It's like good distraction. I've just been very stressful.
Yeah.
Just have to listen to Beyonce on loop. What?
Like, you know how sad it is? I work at a doctor's office and I have to put the home improvement channel because if I put the news, then they just argue amongst themselves in the waiting room. It's sad. And they're grown up.
Right.
Grown people. It's so sad.
Yeah, I've heard it's bad on like Facebook and places like that too.
Well, it got to a point like where if you don't like or agree with somebody else, then you don't like that person. And nobody
Right.
expects another person's opinion that's gonna be different from necessarily what they want to hear.
Yeah. All right, so let's do some chemistry. Just ignore the comments for a while.
We've been ignoring it for too long.
I know, because media does that enough.
It's why we're at this point right now.
All right, so the other part of the lab is seeing if there's radiation from materials, like what kinds of materials can give us, can emit radiation. We talked a little bit about like background radiation, rocks and stuff like that. I do have some minerals here that, you know, just kind of look like normal rocks. And we're kind of pretty. But if we check them out with the Geiger counter, you can see some good radiation coming off of these things. That one, not so much these other ones. So those are just naturally occurring rocks. And the ones that are especially radioactive are samarskite, which is has a lot of rare earth elements, which are the ones down in the 50s and 60s. And as I don't know what else is in there because most of those aren't radioactive. A couple of them are. And then the other one is uraninite, which is where we get uranium from, uranium oxide. And so that's just to note, like most radioactive stuff is naturally occurring. We think of it as this like human-caused, you know, nuclear bombs and that kind of stuff, but it actually all comes from the ground. We refine it and can do stuff with it, but it's all there. So that's some radioactive minerals. And some of the sources of exposure to radiation, like even dangerous radiation, are just like things that you would do in your natural life. Like if you hang out in a lot of caves in certain areas of the world, you're gonna get a lot of extra radiation just because of the geology and what kind of rocks are there. If you go on a lot of airplanes, you get extra radiation because you don't have as much atmosphere protecting you when you're way up high. That kind of stuff. You live at high altitude, those kinds of things. So there's a lot of stuff kind of out of our control in terms of that. All right, anybody know what these things are? Maybe, yes. I think that was funny. Yes, does anybody know specifically what type of stuff it's called? It is ceramic. There's a specific brand that's still very popular. Yeah, is that Fiestaware? Yeah. I don't think there's But
What's so special about it?
it's been around for like forever. I mean, it's like it's basically the same design of dishes that's been around since I don't know the 30s or something, maybe even earlier. It's kind of an iconic like American type of dish, and they're still go to department stores and get them and stuff. But for a while, some of the glazes were radioactive, and so like we got these two kind of red plates. Which color do you like better?
Right.
This one, like vanilla orange. Yeah, you know what? That's so nice because it's radioactive. Yeah.
I would put it back there too.
Radioactive uranium glaze. These were in production 1936 to 1943 and 1959 to 1972. So very cool color, and you get to eat your food off radioactive plates. There is a, where is it? Hold on, sorry, here. There's an information thing about it. So there's uranium oxide in there, which gives it that cool red color. This color is called mango red. Yeah. And somebody actually went through and did the calculations of like how much uranium you're exposed to if you eat off these things. And the basic conclusion is not very much. So even though it seems scary that there's, you know, a radioactive light, the actual answer is you eat off that your whole life, every single meal, and get minimal radiation exposure, like that it wouldn't even really happen. And that's an important, I think that's an important demonstration of the idea that it's not that something is a hazard, it's that it's a risk. So anything can be a hazard that could potentially hurt you, but it's not a risk until you're exposed to enough of it that it could hurt you. I think we kind of sometimes, just in general, default to the position of like, oh, if that thing is dangerous, then I have to avoid all of it all the time. And that's not really accurate. Yeah. We're going to talk about that in a minute. So you guys hold enough for a second, because it depends on the type of radiation and stuff. But in general, yeah, that's a good question. Like for things in general, how much is enough to kill you? So if you're like concerned about, let's say, carcinogens in your food or something like that, yeah, it's true that there are some things in your food that aren't good for you. But how much is it that's actually, how much do you need to eat before that becomes really a problem? Even things like smoking, you know, like there is a level of smoking that does not hurt you. I don't know what it is. It's a pretty small level, but there is a level where it's not really a health risk. The problem is, of course, it's addictive, so you end up exceeding that eventually. All right, so let's talk about two other types of reactions, and then we'll look at the measurements and the half-lives. So the two other types of reactions are called fusion and fission. And this is what we think of when we hear the word nuclear. This is what's the reaction that's happening in an atomic bomb or in a nuclear power plant. And it's kind of different from the nuclear reactions we've looked at so far. It's not so much about decay, it's about bombardment and splitting. So if you hear about like splitting the atom, that's what they're talking about. Fission means to break something apart. So it looks like this. You start with uranium-235. And this is an uncommon isotope of uranium. Most uranium in the world is uranium-238. And uranium-238 doesn't do this. Only this particular isotope does this. So that's why when we talk about different countries getting atomic capabilities and things like that, the main part of that is being able to produce or to refine enough of this uranium. Because you basically have mostly uranium that doesn't do this, known as depleted uranium. And you have to separate the tiny, tiny amount that's only a little bit lighter, that's 235, that does do this. And that's very difficult and very technical. So that's kind of the big barrier to creating nuclear energy. But once you do this, you can shoot a neutron at it. So this combines with a neutron. And then just transiently, it creates this unstable uranium-236. And I'm going to kind of put that in brackets because it doesn't really exist for more than a tiny fraction of a second. The neutron goes in, makes this unstable nucleus, and then instead of that just like spitting the neutron back out to become more stable, it completely splits apart. And it splits apart into a krypton 91, barium 142, and 3 neutrons, and then a bunch of energy. So if we add all that up, it actually works out. (91 plus 142 is 233, and then 3 neutrons is 236. So it still kind of works out. It balances both sides. But in doing this, you've released an enormous amount of energy. And the other thing that is special about this is the products of the reaction is more neutrons. So that's why we call it sometimes a nuclear chain reaction. And that's what ends up happening in something like a bomb. Those neutrons are emitted and can go find more uranium and go split more uranium. And then that emits more neutrons that can go split more uranium. And it kind of keeps itself going until all the uranium is used up and split. And that's why this reaction can sustain itself, even though you need a pretty large amount of energy to get it started, to actually put that neutron in there to start with. So this is what happens in an atomic bomb. Also a nuclear power plant. And a power plant is controlled because what you do is you limit the access of those neutrons to uranium. So you can add or remove the uranium power supply as you need, so that only a small amount is reacting at any given time. And that's how you control it, so that you only get the energy that you need. And that's called nuclear fission. Another type of energy producing nuclear reaction is nuclear fusion. So if fission is breaking apart, what do you think fusion is? Putting together, yeah, to fuse something, to put it together. In nuclear fusion, we take radioactive hydrogen, known as tritium atoms. This is actually a pretty common isotope of hydrogen. You'll see it in things like certain types of watches that glow at night, sometimes have tritium in them if they have these little tubes on the face, like what ones the military uses and stuff like that. They're sometimes used in exit signs, where you can have some radioactive tritium and a screen inside an exit sign, and that means it'll keep bombarding the sign. Doesn't need any power, but it can glow without any light or any power for a pretty long period of time. But anyway, if you can put those two things together, you can make a helium atom and a neutron, and again, a bunch of energy. And this actually makes more energy, certainly more energy per mass than fusion, because you take these tiny little light hydrogen atoms and you can still make a ton of energy. This is the reaction that happens in the sun. This is why the sun produces so much energy. It sustains our whole planet because of this reaction that's ongoing inside there. So why don't we make power plants out of this? Anybody know? If it's lighter, it's cleaner, doesn't make any radioactive waste, why not just do our power plants this way? There's a problem. You know why we can't do it? It requires really high temperatures. So to get this going, you need to heat it above 100 million degrees C, which is pretty hot. It's a lot of degrees. That's the temperature of the sun, basically. So the problem is that it takes so much, and we've done this. I mean, we've done fusion, as people have done fusion. I haven't, but people have done fusion and set up fusion reactors. The problem is you need to put in so much energy just to get it up to the temperature where it can actually react, but the energy you get back doesn't really count. Like, it's not that much more energy. You get a little bit more energy, but it's not really enough to compensate for all the energy you have to put in. One place where you might have seen something like this is a hydrogen bomb. If you've heard of a hydrogen bomb or an H bomb, what happens there is you take a regular fusion or a regular fission atomic bomb, which is like the normal atomic bomb, and you use that to produce enough heat to start this thing going, which is like the second part of it, so for even more energy. So if you already need that much energy just to start this one, it's not really efficient as an energy source. So one of the kind of like magical sci-fi future-y kind of things that people talk about is cold fusion, which is being able to do that kind of a reaction at lower temperatures than 100 million degrees C. And so far that's not been done. Although if you go look on the internet, there's a lot of people who believe that it's like secret and the government just isn't telling us how they do it, but it hasn't been done because it violates the laws of thermodynamics. Someday, maybe somebody will figure something out, but chances are they won't be able to keep it a secret from the world except for the few people who know about it on the internet. So we'll probably know about it. All right, so that's all the reactions that we'll talk about. So know those 5 reactions, be able to complete them and that kind of thing. And there's some practice in the homework for doing that in chapter 5. All right, the last part of the chapter talks about measuring radiation and like how much radiation is coming off of something. And this is basically the answer of 2 questions, or answering 2 different questions. So first, we have units that answer the question, how much radiation is emitted? Like we did with those little things, so we could say how many little counts are coming off of this every minute or every second. And the 2 units that we use for that are the Curie, which is abbreviated CI after Marie Curie, who was one of the first discoverers of radiation or of some radioactive elements. And then, oops, spell that right. Becquerel after Henri Becquerel, another early discoverer of radiation. And we're not going to go into like how many of one is how many of the other, that kind of thing. It's just they're different units. You can convert them just like you convert any other unit. You can practice that a little bit in the homework, but they're both used depending on the situation. Curie is much larger than a Becquerel, so depending on how many or what you're talking about, you might use one or the other. And then other way you could measure radiation is you can talk about, and this is like from a health perspective, how much radiation is absorbed. So you're measuring exposure. How much radiation have I been exposed to, or has this thing been exposed to? So the first one is how much is coming off of the thing, and the second one is how much am I exposed to. So if you're talking about like measuring something, measuring a dose of radiation, that kind of thing, you're probably talking about the first one, how much radiation is emitted from this thing. If you're talking about the health consequences of being exposed to radiation, you're talking about the second one. The units used for this are the RAD, which is radiation available dose, and the REM. And this is the most important one. Stands for radiation equivalent in humans. And the difference in these two, the RAD is like how many particles have you been hit with per like pound of or gram of material. So that's useful like for just generic stuff, but the fact is that humans experience radiation in different ways. Like depending on what type of radiation you're exposed to, you're going to experience that differently. So alpha particles, for instance, can do a much greater damage to the things that they hit. because they're big, they're heavy, they're charged. So when they knock something, they can really cause some damage. So being exposed to a certain amount of counts of alpha radiation is more dangerous than something like gamma radiation. And so that's accounted for in the REM calculation. Now, we have to think about these in a couple different ways, like, because when we looked at the alpha particles, you can see they were just like blocked by air. So if there's something emitting a ton of alpha particles in the corner over there, it's not really a danger to us. And actually, any alpha emitter outside our body is not a huge danger to us because our skin can block it, the air can block it, not that big of a deal. When it becomes a problem is when it gets inside our body. That's when it can cause damage. So when you're talking about like inhaling something that is an alpha emitter, that causes problems. One example of that is radon. Anybody ever had their house tested for radon, that kind of thing? So radon is element 86. It's a heavy radioactive gas, and it's naturally occurring. It occurs on Earth, and because it's heavy, it tends to be down low because it sinks. But what can happen is it can accumulate, and because it's a gas, it can accumulate in your basement, and you can be inhaling it. You wouldn't know it. It's colorless. It's odorless. You wouldn't know that you're inhaling radon. But now you've got an alpha emitter sitting there down in your lungs, and it just kind of sits down in the most sensitive parts of your lungs and bombards everything with alpha particles, and will eventually give you lung cancer, has a high risk of lung cancer. So if you have some sort of basement or lower area in your house, you should always get that tested. You can buy a little kit. I don't know if I think there's some public agencies that will provide those kits as well. You just kind of sit it in your basement for a while, and then you mail it in, and they test to see if there's radon there or not. If there is, you don't have to move or anything, but you do have to put in some kind of ventilation in that basement, because as long as you can circulate the air out, it's okay. But you don't want those things in your body. All right, so that's exposure. And just the average person gets about 360 millirem per year. And there are all kinds of, I think they say it in your book, you don't need to know the numbers, but how much like you're supposed to be exposed to. If you work around a lot of radioactive stuff, like if you're a nurse in a radiation unit or that kind of a thing, you'll have specific targets, and you'll probably, do we have one of these things in here? They'll have you wear like a badge of some sort or a ring to monitor your exposure to radiation, and then you'll send that in every month or something. They'll just make sure that you're getting the appropriate amount of radiation.
Jim, what about lasers? Like,
Yeah.
more and more lasers are being used in medicine nowadays.
Mm-hmm.
Is that also a form of radiation?
Well, remember, any light is radiation. So yes, just like these lights are radiation, just like the sun
But
is.
it's only a concern for your eyes, because you only have to wear special goggles.
Right. Right. So those types of, depending on what kind of light is coming out of them, they could be harmful or not harmful in various ways. So like you could have a ultraviolet laser that is extremely penetrating and potentially damaging that you would have to protect against, but not in the same way as these particles, because that's not going to be penetrating, because it's just light that's going to be absorbed. But you can even, like, you can make dangerous lasers yourself. I don't know if anybody's ever played around with this stuff. Like if you take a DVD burner, something like that, you can take the laser out and you can kind of hook it up to its own power supply, and you can use it to like pop balloons and melt stuff. And people do all kinds of tricks with them. So yeah, there's other dangers from lasers. But this is talking about generally like ionizing radiation. So that radiation that kicks off those electrons. There's a, we've got time. If I can find that. There's a neat radiation chart from this online comic. Okay, we'll kind of go from small to big. And this kind of tells you a visual representation of sizes of doses. So how much radiation you get from stuff. Here are the really, really tiny ones. So just for, let's show you the whole picture just for reference here. If we zoom out on the whole thing, this is, let's see, where's the one? This is a fatal dose down here, even with treatment. So this many orange boxes. This is a usually fatal dose, but can sometimes be okay. This is a severe radiation poisoning that could, in some cases, be fatal. So that's the orange, right? Then you take a couple little oranges and break that down into the greens, and then the greens break down into the blues. So the blues are the tiniest doses. You get radiation just from sleeping next to someone because they have radioactive stuff in their body that's bombarding you, right? Living within 50 miles of a power plant, eating a banana, using a monitor, getting an x-ray in your arm. These are all like small things, dental x-rays. You go on an airplane flight from New York to LA, you get that many blue things. Cell phone is not on here because cell phone does not produce ionizing radiation. So everybody who's afraid of that. There could be other things from your cell phone, but not that. So that much is the same as all the doses. So all the doses in the blue chart combined are 3 little green things. A chest x-ray is 1 little green thing. So that's the point where they will start monitoring you. Like, I don't know if anybody's ever had experience with that, but they'll only let you get a certain number of chest x-rays per year. And then they'll start saying, oh, is this really necessary or not? Because now you're starting to get some bigger radiation dose. So you can see some of these other ones. This is how much you get just from the natural potassium in your body that has some radioactive activity, getting a mammogram, a head CT scan, and this is your normal yearly background dose, mostly from natural sources or medical scans. So that's how much most people get in a year. This is a slightly different unit than from what we looked at. So anything less than that is really not all that dangerous, right? Because that's what you're getting over the year anyway. And then if we look at, this is how much, if you spent an hour at Chernobyl in Ukraine in 2010, a chest CT scan, I think that's what I was thinking of when there's now a considerable amount of radiation because there's a lot of x-rays involved in CT scan. And then if you're working in radioactive stuff, that's how much you're allowed to get for a year because they've determined that there's really no ill effects from getting that much. And then all that in the green chart combined is like this. And you can talk about some of the workers at Fukushima, which is the big nuclear power plant that melted down, was that 2 years ago? 3 years ago in Japan? And then you need about that many of those red boxes to get radiation poisoning, some symptoms of radiation poisoning, if you get that much all at once or like in a really short time. And then you start getting bigger and bigger and bigger from there. And then the really big, if you actually were right next to a reactor core, like at Chernobyl after explosion and meltdown, which people were there, that's how much radiation you'd be exposed to. And that's a lot. So I think kind of the lesson of this, or getting a sense of that, is radiation is certainly dangerous. It can certainly hurt you, and we certainly have to be careful about it. But we don't really need to worry about the small amounts of radiation that we get from things here and there. Again, just because something has the potential to hurt you, there's a dose associated with that too. If you're below a dangerous dose, you don't have to try to avoid every possible thing. So if you say, well, I don't like to go on planes because I don't want to get all that radiation, it's not really a great reason. It's fine if you don't like going on planes, but the radiation is not a great reason because the amount you're exposed to on a plane is a tiny fraction of even just the normal yearly dose. All right. By the way, if you see this one, the target for a nuclear power plant should only release this much per year. The max that a power plant can release is this much per year, which is still just a fraction of what you get just from the natural potassium in your body. So even if you spent your entire time like pressed up against the wall of a nuclear power plant, that is not appreciably increasing your radiation. So you don't have to worry about like getting too close to a nuclear power plant unless it's melting down when you're there, which it should not be doing. Okay, last thing is how do we measure, and a couple people have asked about this idea of the stuff breaking down over time. And that's, we use something called the half-life. And the reason we use this, this weird term instead of just saying how much is over time is because at any given time, either a nucleus has not decayed or has decayed. So it's not like the nucleus partially decays. It's either still this thing or it's turned into this thing. It's one or the other. And that means that when it decays what we call exponentially, which means that it's not just like slowly decreasing linearly. It is either on or off. Let me show you what I mean by that. The half-life definition is the time it takes for half of a substance to decay. So the radioactive elements are always decreasing, but the half-life is how much it takes for half of it to decay. And this can either be measured in mass, like how much of it is left, or radioactivity, like how many curies of radiation, and that's going to cut in half at each time. So let's say we have a particular isotope, in this case, iridium-192. The half-life of this is 74 days. Another way we might write that is T1/2. That's the time for half of it. That's called the half-life. The half-life is 74 days. So that means every 74 days, half of it will have decayed. So if we start with, let's say, 10 grams, after 74 days, we have 5 grams. And then after another 74 days, we have 2.5 grams. And after another 74 days, we have 1.25 grams. So we might say that it took 3 half-lives, or 74 times 3, which is 216 days, to go from 10 grams to 1.25 grams. And this is exactly how you do these types of calculations. There is an equation, because what happens in between the 74 days, but we're not going to get into that in this class. We're just going to look at discrete half-lives. So how many half-lives did it take? And the thing that is, I guess, most confusing about this is you got to cut it in half every time. So like I'll ask this question or something like it. I'll say, okay, you've got 10 grams of iridium-192. It's got a half-life of 74 days. How much is left after 3 half-lives? And a bunch of people will say, well, 10 divided by 3 is whatever, and that's how much is left. But that's wrong. Because we didn't divide it by 3, we divided it in half 3 times, which is a different thing. So 3 half-lives means cut it in half 3 times. And so you cut it in half once, you get 5, cut it in half again, get 2.5, cut it in half again, get 1.25. That's your 3 half-lives. All right, so let's try that. Same idea. I'm just going to flip it so that we can also look now at the radioactivity. So let's say we have a sample of the same stuff. let's say we have an activity of 8 times 10 to the 4th becquerels. What is the radioactivity after 148 days? So how do you do a problem like that? First thing you gotta look at is you're given a time, so you've got to figure out how many half-lives is that. Because once we know how many half-lives it is, we know how many times to cut it in half. So how many half-lives is 148 days? 2, yeah. Because each half-life is 74 days, so 2 is 148 days. So that tells us that this has undergone 2 half-lives. So how do we figure out what the radioactivity is after those 2 half-lives?
Divide 8 times 10 to the 4th by 2 twice.
Yeah, divide 8 times 10 to the 4th by 2 twice. So if you divide it by 2 once, you get 4 times 10 to the 20, 4 times 10 to the 4th. Divide it in half again, you get 2 by 10 to the 4th. So and depending on your comfort with this stuff, it's up to you. I always recommend setting up a little chart like I did above. So I'd go 8 by 10 to the 4th. And then you cut it in half and get 4 times 10 to the 4th. Cut it in half again. Another 74 days. 2 times 10 to the 4th. And so then the total two half-lives, cut it in half twice. All right, think you can do that? Okay, let's try another one. So now we're going to look at technetium-99m. We talked about that before. It's good for scanning organs. It has a short half-life and is a pure gamma emitter. So the half-life is 6 hours. Okay, much shorter half-life than the 74 days of the other one we just looked at. So this question says, suppose 80 milligrams were prepared in the morning. How much is left after 24 hours? See if you can figure that out. How much is left after 24 hours? If 80 milligrams prepared in the morning. Figure it out. 5 milligrams. Sound good? Yeah. Let's set up that chart again. So 24 hours is how many half-lives? 4, right? 4 half-lives. So that means we got to go 80, whoops, not 8, 80, and then to 40, so that's 1. Another 6 hours gets us to 20. Another 6 hours gets us to 10. And another 6 hours gets us to 5. So 24 hours, there are 5 milligrams remaining. Right? So common mistakes with this, I already told you about the one. So I might ask a question like this and somebody would divide it by 24 or divide it by 6 or like assume that there's just one calculation that you do to get to the end. And remember, it means you have to cut it in half a bunch of times. So remember to cut it in half a bunch of times. And then even if you kind of know what you're doing, I would recommend that you at least write out some amount of like how many times you're cutting it in half, because it's easy to not count the first one, to like start at 40, to go, okay, 40 to 20 to 10, and then like call that 4, because you start, or you go like 80, 40, 20, 10, 4 half-lives, but that's not actually 4 half-lives, that's just 4 numbers because you started at 8, so you gotta count the half-lives out. And if you find some way that you can write it out that makes sense to you, that's probably helpful. All right, so the other thing to note about this, if we go back to the lab, this is a, oops, go back to the lab. This is a common mistake. So take a look at this problem. Cesium-137 is a radioactive isotope, and it undergoes beta decay to make barium-137. We tend to think about half-life in terms of like something disappearing, but it doesn't really disappear, right? It decays, it turns into something else. So in this particular problem, it says, all right, the half-life is 30 years. Assume you start with a 64-gram sample. So at time 0, when you start, you've got 64 grams of this and 0 grams of this, because you just have your 64 grams of your cesium-137. So then after 1 half-life, what do you have? After 30, yeah. So after 30 years, that's 1 half-life. So you've got 32 grams of this. What about the barium? Right, also 32, because those extra 32 grams didn't just disappear, they became barium. So when it decays, it doesn't just like vanish, it becomes something else. So then what happens after another 30 years? Yeah, you've got 16 grams of cesium. What about the barium? Right, because those additional 16 grams have now turned into barium, and so on. And so when you plot this, when you complete this lab, you'll see these kind of 2 curves that end up crossing kind of like this. One thing is going up and the other thing is going down, and they're not linear. Linear means you change by the same amount each time, but this is changing by a changing amount each time. So it goes 64 to 32, loses 32, then loses 16, then loses 8, then loses 4. So that is a curve that looks more like this rather than a straight line down. And as we call it, an exponential decay. If you're curious about it, there is an equation that you can look at in the book that like how you actually figure out what if it isn't an even half-lives, what if it's like 35 years, what would happen, you know, how much exactly would you have? You can set up an exponential equation. It's like a 2 to the n type equation, or 1 over 2 to the n type equation. And if that's how your mind works, you can go there. But if not, don't worry about it. This is cutting in half, it's fine. So any questions about this stuff? Okay, that's it. That's nuclear chemistry. So, yeah. And we did a lab tonight too, so it's pretty good. Pretty good night.
Yeah.
I know that you wanted to go into one of those problems in the lab.
Oh yeah, thank you. If you haven't completed your labs yet, let's do this real quick. Sorry, but you probably want to do this because it's an annoying problem. No, it's good, because otherwise nobody would know what to do for Wednesday. This is from yesterday's lab. Save that. I'll put this in the notes folder as well so you can see the calculations. All right, so the last question of this lab is something that, nope, this is the wrong lab. This is right, this is the old one. Again, sorry, number 9 is what we want down here. Here we go. Time. All right, right here. So you can figure out all these kind of general calculations about, or general questions about like what is isotonic and all that stuff. But this last one, a little more complicated calculation, so I didn't want you to do it on your own. First of all, these equations, I'm not sure exactly the right way to write them, but basically you're just saying what does sodium chloride do when it dissolves in water? You take sodium chloride and you form sodium ions and chloride ions. And when glucose dissolves in water, it's even simpler than that. Nothing really happens except it becomes aqueous from being solid. So I think that's the best way to write those equations. I don't think you should put actually water in there. But the important thing to note from that is that when sodium chloride dissolves in water, it forms 2 particles. When glucose dissolves in water, it's just 1 particle per particle of that. So 1 mole of NaCl actually forms 2 moles of ions, because it forms a mole of sodium and a mole of chloride. But 1 mole of glucose just forms 1 mole of glucose in solution. So that means that these numbers are going to be a little bit different. Molar concentration is moles per liter. So this is where the calculation gets a little bit beyond what we would do in class. But M over V means mass per volume. So that means 5 grams per 100 milliliters, because it's percent, so per 100. So 5 grams glucose per 100 milliliters of solution, not water. We want to convert that to moles per liter. All right, so C6H12O6, I'm just going to use the internet to help me out here. Type in 5 grams of glucose, which is 27.8 millimoles. If you want to do some practice calculating moles from grams, you could do that. We'll do that a little more quickly. And then that's our liters. So now, instead of grams per milliliter, we've got moles per liter, which is molarity. And if we calculate that through, we get 0.278 molar. Okay, so that's the molar concentration of 5% glucose. All right, now we're going to do the same thing for NaCl, but it's 0.9%. So that's 0.9 grams per 100 milliliters. Again, we're going to go to moles. So we're going to go 0.9 grams NaCl. 15.4 millimoles. Okay, so that's 0.154 molar. NaCl. And then the molar concentration of the sodium ions and the chloride ions is the same because it's 1-to-1 based on the equation. So 0.154 molar sodium ions, 0.154 molar chloride ions. And then here's where it gets a little interesting. The total concentration of dissolved ions then is those added together. Okay. So then that last question where it says, do 5% glucose and 0.9% NaCl have approximately the same concentration of dissolved material? They do, because the molar concentration of glucose is about 0.3, and the molar concentration of sodium chloride, because we should really be using just one figure, is also 0.3. The total concentration of ions, of dissolved materials. That's important from an osmosis standpoint, because both of those things are going to be isotonic. Because 0.3 molar is like the magic isotonic concentration. That's the intracellular fluid concentration of particles. So even though the concentrations look different, 0.9% versus 5%, so 0.9% is sometimes called normal saline, and 5% glucose, those are actually the same, those are going to have the same osmotic pressure. Those solutions are both going to have the same osmotic pressure. They're going to be isotonic to the blood cells. And that's why those concentrations are kind of special. 0.9% NaCl and 5% glucose have approximately the same particles dissolved in concentration. So that's what that question was about. Thanks for reminding me. Does that make sense? Maybe? You don't have to be able to do those calculations, but that idea that it's the molar concentration that matters because it's the number of particles per volume, not the mass, that determines the osmotic pressure. All right, so that's it. Thanks, everybody.